Welcome to another video for physical science. In this video, I'm going to be discussing the differences between weight and mass. So your formula for weight is mass times gravity. What does that mean? Well, I'll explain that as we go along. And as I go along, let me first explain what mass is. So mass is a physical quantity expressing the amount of matter in a body or an object that I'm referring to. So that means I'm referring to the amount of atoms or matter that something is comprised of. It is the measure of the body's resistance to changes in velocity or inertial mass. Okay, so something that has more mass, like an 18-wheeler, will be much more difficult to stop than a teenager on a skateboard. Okay, so we're talking about the amount of matter or atoms or compounds that something is made out of. And also, it is a force experienced in a gravitational field. Okay, so mass remains the same no matter where you go in the universe. So if I am on Earth, if I'm on the moon, my mass remains the same. It does not change. Okay, so if I'm looking at this astronaut, I'm seeing that he's 68 kilograms. Well, on Earth, he's 68 kilograms. That's his matter. That's his mass. And if we take him to the moon, he's exactly the same, 68 kilograms. He does not change. So for example, let's say on Earth, or on the moon, since I can weigh less, that's probably the easiest way to lose weight, right, is to travel to the moon. But if I'm on Earth and I have love handles and I go to the moon, I'm still going to have those love handles, okay? Those are still going to be there. My mass will remain the same even though my weight might change. So if I go anywhere in the universe, my mass will remain the same, okay? So let's talk about weight. So mass is something that doesn't change, right? But weight is something that does. It's relative to where you are on Earth or even on in the universe. So for example, because the gravitational pull of Earth pulls you towards the center, the closer you are to the center of Earth, the greater the gravitational force will be felt. But if you're, let's say, in Mount Everest, you're actually going to have gravity is actually exerting less force on you, so you actually would weigh less. But it's so minuscule that you don't really consider it that big of a difference, so it's irrelevant really. But in any case, it's still less of a force that you're feeling the further away you get from the center. So the force that gravitation exerts upon a body is equal to the mass of the body times the local acceleration of gravity. So this is my formula for weight. It's mass times my local acceleration for gravity. What do I mean by that? Well, what do I mean by g? It's little g here. It's a vector quantity. It's a gravitational force of an object. So everything has gravity. The greater mass that you have, the more gravity you're going to have. The more gravity you're going to exert on another object. Technically, you also have gravity. Each person around you has gravity, but again, it's so minuscule that it's not really something that we consider in physics. So which is related? Little g is related to the mass of the objects. Okay, so the greater the object, in other words, the greater the mass of the object, the more g it will have, the more gravity. So we don't really worry about how much gravity a person has or even a vehicle or anything like that. We're talking about things that are massive like planets and satellites like a moon and orbiting objects like that. So the Earth's mass is about 81 times more than the moon, which means it has a greater gravitational field. Okay, it has a greater ability to keep things within itself. That's why buildings and people don't fly off the planet because the gravitational field of Earth is keeping everything grounded. Okay, and that's also why it has an atmosphere and the moon doesn't. So Earth has a greater gravitational field. In fact, Earth's gravitational field is so strong that it keeps the moon in orbit around itself. So the gravitational field, the quantity of this g that we're talking about for Earth is 9.8. And for the moon, it's 1.62. And that's related to the fact that the moon's mass is much smaller than the Earth's. Okay, so when you go to the moon, you're not going to feel as much gravity. But if you go to Jupiter, it's 24.8 newtons per kilogram. So it's considerably bigger, and of course, Jupiter is much bigger than Earth as well. So moonwalking versus walking on the moon, right? So if I'm walking on the moon, like I mentioned before, you're going to experience less gravity. That's why you see the astronauts look like they're floating around. That's because there isn't as much of a gravitational force pulling on them. Michael Jackson, the greatest moonwalker ever, as smooth and light on his feet as Michael Jackson might be on Earth, he is still not as light. He's still not as light as an astronaut on the moon. Okay, you can see them hopping around there with ease. All right. But in conclusion, to find the weight of an object, you need to find its mass, and you need to have the gravitational field of the other object that it's in contact with. So here's a problem that we can cover here, discussing this. So if an astronaut has a mass of 112 kilograms, what is its weight? What is his weight on Earth, the Moon, and Jupiter? Well, if we have a mass of 112 kilograms, and we have the g's of our different planets, we can use these g's to input into our formula, W equals mg. So my mass is 112, my g for Earth is 9.8, and my weight, the force that I apply on Earth is 1,098 newtons. Okay, likewise for Jupiter, my mass is still the same on Jupiter, but the g's are different, 24.8. So I have a force of weight of 2,778 newtons. And then for the Moon, 182, because it is the less massive of the three bodies, I'm going to have less weight there. Okay? Well, I hope this was helpful in finding weight of a weight of an object as compared to its mass. And as I finish up this video, I'm going to leave you with this little extra, if you will. Good luck with your studying.